morning, we have three presentations, two real ones, one from Mark Cairnie and one from Jet-Impingement. And then I'll make the third announcement at the end. So please stay here after we finish with Jet-Impingement. This session is continue with the packaging integration technologies. In the morning earlier, we have heard from the semiconductor presenters, Yu Hao Zhang and his students, and then go up to the board level by Matthias Spiller, and Orlando Burgess. And now we would then move a little bit deeper into the packaging with the flavor of thermal management. And that is the work of Dr. Christina DiMarino and her student, Mark Cairnie. And we'll end the session, go back to basic British materials, with also packaging with material flavor by Dr. Qiju Lu and his student, Dr. Chen Zhang. Mark Cairnie, let me say a few words about Mark. Mark got his bachelor from Penn State in 2019. Okay, and then he came here as a Bradley graduate fellow between 2019 and 21, when he received his master's degree with Dr. DiMarino doing work the packaging. And then he entered the PhD program, and as a PhD student, continue working with the medium voltage integration and of course thermal management. And his research has been funded by ECE Department, Bradley Fellowship, and also by the APA-E project. We have one APA-E 2018 and now 2021 open, both opens. And so he's architects behind these big projects. So please, Mark.
Good morning, everyone. So today I'll be talking about a 10 kV silicon carbide MOSFET module with double-sided jet impingement cooling. Oops. Mouse isn't working, Matt. There we go. Cool. I think we're good. Thank you. So the outline for my presentation is I'll start off with a brief introduction. We'll review some of the motivation for the work. I'll then go into a module overview and we'll discuss some of the cooling strategy and the module fabrication steps. And then I'll wrap up with some experimental results. So to kick things off, I don't think I need to rehash the growing interest in medium voltage silicon carbide devices, at least not with this crowd. I think Dr. Mathers from NREL yesterday did a great job in his keynote or his tutorial kind of discussing some of the emerging applications for these sorts of technologies, be it high voltage grid tie inverters or some of these back-to-back medium voltage converters that he discussed. There's certainly a growing interest in the research community to explore these devices and understand what's the most beneficial use case for them. So I think we've passed the application inception stage. I think we understand where we'd like to use this device. We have some ideas, but actually getting to the demonstration stage is a little bit trickier. So there's been a lot of projects within CPES and within the academics to develop system level demonstrators for these 10 kV silicon carbide devices. And while I haven't had the privilege of working on some of these projects, I have been able to observe them over the last couple of years. And being one of the packaging students down here in Blacksburg, my colleagues have been quite vocal about all the improvements they would like to see in 10 kV silicon carbide packaging. So to name a few, there's certainly some insulation reliability concerns. People have been talking to me about that. System integration has been a challenge historically. If you do manage to solve the insulation problem on the module, once you bolt a bus bar and a heat sink to it, that changes the insulation problem. So we're concerned about system integration. We're concerned about thermal performance, parasitic inductance, mechanical ruggedness, the usual suspects. There's also been issues with fault tolerance, cost, and availability of these devices. So quite a broad range of issues. A couple things that aren't on here are spontaneous combustion. This has been a problem in our lab, as well as what I call RUD events, or rapid unplanned disassembly, when the converter components go flying across the room. So these are a couple issues we'd like to mitigate. And as much as I'd like to talk to you all about how I'm going to solve all these problems here in the next 16 minutes, my work is really a small piece of a much broader effort at CPES to try and address these sorts of challenges. So I'm going to do a deep dive here a little bit on some thermal performance issues, specifically this double-sided cooling, and talk about that within the context of the insulation problem. So I'll start out with some trends in low voltage packaging, where I think we've seen a very clear trend towards higher thermal performance, specifically when it comes to DSC. And I think this has been motivated largely by kind of the rapid adoption of 1.2 kV SiC within the automotive industry. So in 2004, we had, fairly straightforward packages that were being used in the Toyota Prius. By 2010, in the Chevy Volt, they had moved to double-sided cooling and direct substrate cooling. By 2015, we saw introductions of jet-impingement cooling on electric vehicles. And most recently in 2018 on the Audi e-tron, they've gone with a double-sided, actually, immersion cooling system. So a very clear trend in the low voltage path. For medium voltage packaging, the path is a little bit more sporadic, and this is partially motivated by kind of this broad spectrum of issues that we have to deal with. So I think the Cree module in 2015 was one of the first to kind of go after the induction problem. They had some very low inductance coaxial gate connections they developed. They also took the insulation problem very seriously on the outside of the module. In 2018, CPES and the University of Nottingham collaborated on a 10 kV module that I think was the first to hit the kind of trifecta of low inductance, cooling, and the insulation problem. And some of the more recent work from CPES in 2022, which has come from Zishen when he'll be presenting next, has used some nonlinear field grading to attack some of the insulation problems. So a bit of a more sporadic trend, perhaps, in the development of medium voltage packaging, but certainly a theme of single-sided cooling. To my knowledge, I haven't seen double-sided cooling applied at this voltage level before. So the research objectives for me are to kind of build on the existing work from CPES and the University of Nottingham on 10 kV packaging, but kind of combine that with the proven thermal performance improvements from double-sided cooling to develop a double-sided cooled 10 kV package. So next, I'll briefly go over some of the module details. So this is a phase leg module that's based on third generation 10 kV silicon carbide from Wolfspeed. We've got 4 devices in there total, 2 in parallel per switch position. So you can see an exploded view of the module here on the right with the 4 devices located inside. These 4 devices are sandwiched in between 2 aluminum nitride substrates that serve as the top and bottom cooling surfaces. So the devices utilize a molybdenum post interconnect in place of more conventional wire bond technology. So this is really what's enabling us to pull the heat out of the top of the die and exhaust it through that top substrate. You'll also notice that we actually have these die kind of flipped around a little bit. So some of these die are mounted on the bottom substrate. Some of these die are mounted on the top substrate. And part of this is an electrical routing issue. Because this is a phase leg structure, kind of alternating the die placement like this makes it a little bit easier to do the electrical routing. But it also allows us to kind of share the heat flux between the top and the bottom side cooling surfaces. So if we have any mismatch in the heat flow from the top and bottom, flipping these things around gives us symmetric heat flow so we can get the best utilization out of our coolers. So in terms of this post interconnect, there's kind of some interesting trade-offs that emerge when we talk specifically about the height of this interconnect. Part of it is an insulation problem. Because this is a vertical silicon carbide device, we end up with a voltage or a potential difference between the top and the bottom substrate. And so as we reduce the height of this post, those 2 substrates move closer together and result in electric field crowding on the edges of the substrate. So from an insulation standpoint, we're motivated to make that post as long as possible. Of course, that's counter to what we would expect for or what we would desire from a thermal performance standpoint, where we want to minimize the height of the post to improve heat sharing between the top and bottom substrate. So what this plot on the right is showing the electric field intensity as a function of that post height, and also the junction to case thermal resistance as a function of post height. So you see these kind of competing physics. What's interesting to me is that the junction to case thermal resistance isn't the whole story. Once we get the heat to the case, we also have to exhaust it into the ambient. And so if we change this picture around a little bit and instead look at the junction to ambient thermal resistance, so now this plot becomes a 3D plot where we're looking at the post height on the x-axis and the heat transfer coefficient on the y-axis. We see that the effective junction to ambient thermal resistance is actually a strong function of HTC, and not as strong a function of the post height. It doesn't really become a function of the post height until we get into excess of 100,000 watt per meter squared Kelvin. So this is partially what motivates the decision to go direct jet impingement, so we can get these higher heat transfer coefficients and get down to a range where we actually see that sensitivity. So next, I'll talk a little bit about the cooling strategy. So this is a schematic drawing or a representation of a single-sided cooled module, and kind of represents the kind of typical module you might find at this voltage level. So it's got a cold plate at the bottom, terminals on the top. And this is convenient because it allows us to maintain kind of the creepage and clearance distances, not just between the terminals, but also between the terminal and the base plate. Now this picture starts to get a little strange once we add a second cooling surface on the top. So now we need to move the terminals to the side, and we have to honor that creepage and clearance distance between the terminals and the base plate. So this starts to set kind of a lower bound on the power density we can hit. You can imagine as the width of this cold plate starts to go to zero, the overall length of our module is about twice the creepage distance. That's kind of the lower bound on what we can do. So part of our strategy is to actually integrate these coolers directly into the module. And when we do that, we end up with a shape that looks a little bit like that. So now these coolers have been moved inside the module, and we don't have to worry about that creepage and clearance to the cooler itself. We're now only concerned about what happens between the terminals. So this allows us to kind of decrease that lower bound on the energy or on the power density. But the cold plates aren't the whole story. If you look at the kind of implementation, or the conventional implementation of low voltage DSC, say in a power or a vehicle inverter standpoint, it usually looks a little something like this, where they have these stacks of modules and coolers. So they'll kind of alternate cooler module, and they have to compress this whole stack together. So it's not just about the cooler, it's about all this fixturing that goes around it. And so when we're going to talk about creepage and clearance, we may have gotten rid of the cooler problem by integrating that, but ultimately I still have all this clamping hardware that goes around it. So part of the strategy by integrating these coolers is also using a one-piece housing. And the idea here is that we no longer need compression to get a good thermal interface between the cooler and the module, because the cooler is now integrated into the module. But that's not the only reason for compression. There's kind of two reasons for this compression. One is to get that thermal contact. The other one is actually to apply or to provide mechanical support to the module. And that's a bit of an open-ended piece in this work. So in theory, we could get away with a one-piece housing. It's been demonstrated in the 1.2 kV world before, where they have a one-piece aluminum housing and they don't need external clamping or fixturing to apply pressure to that. In this instance, it's a little bit harder to evaluate. What I can tell you is we built this, we've tested it, and it seems to work so far. But as we start to push the performance, we'll see what the limitations are on the amount of clamping force that we can get away with. So here's what this looks like, kind of taking this back into 3D for a minute. So this is the assembled module that you can see here in the cooler and the two halves of the cooler. I called it a one-piece cooler earlier. It is a one-piece cooler. We manufacture it in two, though. Eventually, these will get epoxied together. And in my experience, the epoxy bond on this 3D printed material is actually stronger than the bulk 3D printed material itself. So it effectively acts as a one-piece housing after it's assembled. And here you can see a cross-sectional view of these cooling channels that are printed into the housing, and how these jets are able to impinge directly on that substrate and give us that direct substrate cooling. So next, I want to talk a little bit about insulation impacts inside the module. The primary focus of this talk is cooling performance, but if we can pick up some benefits to insulation along the way, or at least be mindful of the implications to insulation, that's a benefit. So I want to talk a little bit about the kind of the triple points that form inside the module. And a notable one is this triple point here that occurs in the air. And usually the way this is mitigated in kind of conventional medium voltage packaging is with the addition of a base plate. So by adding a base plate to the module, you can now fully encapsulate the entire substrate and encapsulate both the top and bottom side triple points to get a little extra performance out of the substrate. What I'm proposing is a little bit different. I'm proposing that we can fully encapsulate the substrate, but do it without a base plate. So the benefit here is we kind of we get rid of some of the reliability concerns associated with the large area bonding, but we maintain this fully encapsulated substrate. So if we look at that from a simulation point, if we look at the first case here, what you're looking at in this simulation is a single substrate with an electrode on the top and bottom, but we have the silicone encapsulant on the top. and the air on the bottom. And this is a fairly symmetric structure, so the electric fields form somewhat symmetrically, but we end up with about 7 times the breakdown strength of, or the electric field with about 7 times the breakdown strength of air. So you're certainly going to get partial discharge here. Once we encapsulate both sides, we're now on the order of 1.3 times the breakdown strength of silicone and about 0.8 times the breakdown strength of silicone. So we're getting closer to the safe region, but one of the problems this base plate causes from an insulation standpoint is it causes an asymmetry in the formation of the electric field. And you can see that with these relative breakdown strengths. So by removing the base plate, we also remove this asymmetry in the electric field. And oops, there we go. So we remove that asymmetry and we maintain this nice symmetric electric field, which means both the top and the bottom side of the substrate have an electric field strength of about 1 times the breakdown strength of silicone. So we're able to eke out a little bit more thermal or a little bit more electrical performance out of this than you might normally be able to do with a base plate. And this has been experimentally verified. So I partial discharge tested these substrate samples at our lab in the basement of Whittemore and found that we were able to do about 13.2 kV PDIV at 60 hertz on these substrates. So sufficient for 10 kV operation. Last thing I'll touch on here with the modules, some considerations in regard to the terminals. So the way the terminals were designed here is to actually use a water jet silicone gasket. So these silicone gaskets seal in between the spring pins of the module and the module housing. This helps with the encapsulation process. We need a way to kind of contain the encapsulant inside the module when we pour it in there. And that's a little cumbersome considering there's holes on opposing sides of the module. So this silicone gasket helps with that. It also helps to keep debris out of the encapsulant. The encapsulant can kind of result in a bit of a sticky or tacky surface, which can pick up dust and particulate from the environment. And those can cause insulation concerns around the module. So this terminal has been designed with these spring pins so that it can interface directly to a PCB bus bar. So this is kind of an exploded view that shows the spring pin passing through this water jet gasket and interfacing into a PCB bus bar. And we actually use the housing and the PCB bus bar to fully enclose this terminal and break any in-air paths between terminals or between the terminals and other metal components in the system. So this is what that looks like in hardware. So you can see the double-sided cooled module here in the center with the bus bars on opposing ends to mate with those spring pins. So kind of a summary of some of the ideas I've talked about here. Some of the key benefits of this approach are we've integrated the coolers, which kind of reduce the creepage and clearance needs. We've also moved to kind of a one-piece housing strategy, which should help us reduce some of the clamping and fixturing needs. We've managed to delete the base plate and also remove these in-air triple points. So keep all those really critical insulation points inside the encapsulant, but without taking on the overhead of the base plate. And we can also utilize this 3D printed cooler to kind of create a high density PCB bus bar interface. So last, I'll touch quickly on some module fabrication steps. So this module is fabricated entirely in our packaging lab on the 6th floor. During the dialogue session this afternoon, we'll be offering tours of the packaging lab. So if you'd like to see some of these samples closer and see some of the processes we use to put this together, we'll be happy to show you that during the dialogue session. But this is what the die looks like with the molybdenum post centered to the top. So most of this goes together with silver sintering. So the posts are silver sintered to the top of the die. And then the dies are individually characterized after each step of the fabrication. This is kind of a byproduct of having to assemble this by hand. So I track the performance of the device throughout each packaging step to make sure it hasn't degraded, make sure I haven't damaged it or mishandled it, which I have a tendency to do with the lack of sleep that I run on. So this is a look at what the RDS-on at the bare die when we get the die from the manufacturer and after the posts have been attached. And this is something that we track throughout the process. So after that has been, after the posts have been mounted, these can then be centered down to the substrate, same sort of silver sintering technique. And then finally, we attach the terminals to the module. So the terminals are actually soldered on, and we use a molybdenum post. It's made of 2 components. There's a commercially available spring pin we get from Milmax and a custom molybdenum post. So the molybdenum post is centered down to the substrate, and then the pin is soldered into the post. So that's what kind of the low current gate and Kelvin terminals look like, and then the larger power terminals to actually conduct the drain current. And once the modules have been, or once the terminals have been attached, the sandwich structure can be assembled and then potted into the housing as you see in the top right. So moving on to some quick experimental results. I won't hash out the junction to case thermal resistance measurements. I think Matthias gave a good overview of that in his presentation. The extra piece that I have on this is I'm also interested in junction to ambient thermal resistance measurements. So it's the same piece of equipment he used. The difference is we have an external chiller with an inline flow meter and regulator, and also an inline temperature or thermal couple to measure the ambient temperature. And this is operates exactly the same way that he proposed, where we use the device itself as both the heating element and the temperature sensor by characterizing the forward voltage drop of the body diode as a function of temperature. So we can heat up the device by conducting through the channel, shut the heating current off, and measure the forward voltage drop to detect the temperature. So there's 3 measurements in total that I took on this system: 2 junction to case thermal resistance measurements, one from the bottom side here and one from the top side, just like Matthias did, with the extra addition of this junction to ambient thermal resistance measurement for the total system. So once I have these 3 measurements, I can combine them into an equivalent thermal resistance network to understand the complete system. And what we found is that we have an effective junction to ambient thermal resistance per switch position of about 0.44 K per watt. And that's at a fairly conservative 0.6 liter per minute flow rate. The cooler was designed for a little bit faster than that, but I'm walking it up slowly because I want to see what happens. So we're starting out slow at 0.6 LPM, and as we go on, hopefully we can get this up to 2 LPM. But at that 0.6 liter per minute flow rate, we're at about 7.4 kilowatt per meter squared Kelvin, or 7.4 kilowatt per meter squared Kelvin effective HTC. This is a look at some of the static characterization results. The only thing I really want to point out here is the discrepancy from what we expect the module to be, the 156 milliohm RDS(on), compared to what it actually is, which is about 168 milliohm RDS(on). So I did some work trying to tack down where exactly we were picking up that stray resistance, because it's a little bit higher than what I predicted in the simulation. And what I found is that we're picking up about 8 milliohms from the spring pins. This is probably the largest contributor to the stray resistance, and probably the biggest area that we could improve this if we wanted to get this number down further. One of the constraints I had to operate in was using a commercial off-the-shelf spring pin. So if we open up the door to custom spring pins, larger diameters, stiffer springs, this is hopefully a number we could get down. The last thing I'll highlight here is some double pulse switching tests that we did. So this is what the completed module looks like between its 2 PCB bus bars, and then it's got a gate driver board mounted on either side for the high side and low side switch positions. And during my testing, I got this up to 3 kV, a bus voltage of 3 kV with a 60 amp load current and a maximum slew rate of about 160 volts per nanoseconds, which is awfully snappy. I don't think you'd ever want to run this that fast, but I was curious how fast we could go, and that's how fast it got. So that's with about I think about a 300 milliohm external gate resistor. So with that, I'll wrap it up. Some key achievements here is that we've demonstrated a 10 kV, 168 milliohm silicon carbide MOSFET package. We've got an effective theta JC of about 0.9 K per watt. So that's that junction to case component. The junction to ambient with the cooler is about 0.44 K per watt. If we get that HTC a little bit higher with the higher flow rates, theoretically, we should be able to support about 200 watt per centimeter squared over that experimental theta JC. And so at that 0.6 LPM that we looked at, the housing integrated jet-impingement coolers achieve an effective HTC of a little over 7,000 watt per meter Kelvin. So some area improvements, I think, are some maybe potentially stronger materials for the additive manufacturing. We're leaning on that 3D printing quite a bit. And so any improvements in the additive manufacturing realm will translate to improvements here. The other thing I think is important that I pointed out is also these spring pin terminals. I think those represent kind of a barrier to further reducing the stray resistance of the package, and also will be a barrier to further current scalability of a structure like this. So with that, I'll leave it there. I'll be at bench 68 during the dialogue session. So if you'd like to see this hardware in person, feel free to stop by my bench. Thank you so much.